The next topic that we are going to discuss, it will be linear transformations. Now, linear transformation are first of all, let's try to make a connection with the previous topics that we have covered. So far, we have discussed the basis, okay? So we can have different bases, which is as simple as trying to distinguish whether we're going to use this basis or this basis. There is a pair of vectors which are linearly independent, and they both can do the job perfectly. Now, we have bases, and we have also coordinates. So, once we have a basis of the coordinates would be the projection of the specific vectors onto different bases. And now, today, with this information that we already have, we are going to discuss linear transformation, or LT, which will make us possible to transform from one basis to another. Okay? So if we have a standard basis like this one, we can try to represent the same vector, the same solution, the same data set, the same data distribution, but looking from a different domain. And in order to do this, we have to first give the definition of linear transformation, which we are going to call it LT or T. And these T's, or these linear transformations, they can be described also with an equivalent matrix. So whichever way we are going to modify a vector or another matrix, we can represent it by implementing a linear operator, which is the matrix itself. And after we're going to discuss a little bit about the linear transformations themselves, we're going to see how we can apply these into changing the basis. Now, the moment that we change the basis, the next big question, which we are going to discuss in the next 2 or 3 sessions, it would be, the biggest question would be, which one is the best basis? So we can have this, or we can have this other basis that is going to look like this. Which one is the best basis? This is the biggest question. And we're going to learn this one, that the best basis, but we don't know this yet, we'll cover it very soon. But I'm just offering this information now, because when we go to the diagonalization of matrices, I'm going to repeat this 2 to 3 minutes piece of material, both as a review, and also with the intention that we understand it correctly and completely. So the best basis, it will be one which is composed of eigenvectors, okay? And eigenvectors, there are some respective vectors which can be associated with matrices, and where the matrix does preserve specific properties. Now, let's continue here. So we have the linear transformation. The linear transformation, they have respective matrix representations. And first of all, let's see an example, or let's say the following. The linear transformations, they are described as follows. Txy, this is equal to x plus y, x minus y, 2x plus 3y. Okay, so this is a linear transformation. This is how we describe these. And in fact, an important question is the following. What is the matrix A which corresponds to this linear transformation? What is this? This is a common question that often might come up. In order to determine this, what we do is the following. A is going to be equal to column 1, column 2, and column n, and all of these columns will be equal to, so these are all columns, will be equal to the linear transformation on E1, linear transformation on E2, and linear transformation on En. Okay? So what this means is that we can apply on this linear transformation the standard basis. So E1, E2, E3, we know what they look like, and let's try to determine the respective matrix which conducts this linear transformation. So initially, let's apply what is T on 1, 0. This is the standard basis, right? What is it? This is going to be equal to, we have 1 plus 0, 1 minus 0, 2 times 1 plus 3 times 0. Let's see what we get as an answer. This will be 1, 1, 2. Okay, so we got the first column, and then we have to apply the same linear transformation on the next standard basis element. We have here 0, 1. This is 1 minus 1 and 3. So then the matrix A, it is going to be, so combining these two columns and following this reason that we have here, let's continue this here. The A, for this specific linear transformation provided here, is going to be 1, 1, 2, 1 minus 1, 3. So this is 3 by 2. So 3 rows and 2 columns. And then, and let's see if this is true. It's always good to check. So let's see what we get. A times x. And this is equal to 1, 1, 2, 1, 1, 2, 1 minus 1, 3. And this is again 3 rows, 2 columns times x, which is 2 by 1. And this is going to be equal to, let's do this. And in fact, this 2 by 1, let's write this as x and y. And here we have x plus y, x minus y, 2x plus 3y. We notice that we have the same answer, and it looks like in good shape. So this is 2 by 1, and this is 3 by 1. This is the standard way to find the matrix representation for a linear transformation. Now, we could also do the following. If we see here, we can factor out the value x, and this can be 1, 1, 2. And here we get here plus y times 1 minus 1, 3. So we observe that this is clearly going to be the same thing, and we can equivalently write this one, because when we have discussed in the class regarding the range of a matrix, we know that the range of a specific matrix, it corresponds to the linear combination of the columns. So, pra potrzebuję kolona, combinazione lineare di due colonne è range, so it gives an answer for any other vector. We have here 1, 1, 2, 1 minus 1, 3 times x, y. So we could extract this matrix also looking at the values here, or using the formal approach, which is trying to apply the linear transformation on the standard basis. Another good example, which
Because the eigenvectors were the ones 1 and 0 after the transformations, and 0 and 1 after the transformations.
Say it again, sorry?
What were the eigenvectors?
Eigenvectors. We don't know this yet. We're going to learn in the next 2 or 3 sessions, okay?
Oh, okay.
So, let me think. Yeah, but just I'm going to remind you, when we come to the issue of eigenvectors, I'm going to repeat to you again that the essence of linear algebra is all about being able to change the basis or transforming the data set. So, it is unacceptable that you would go in 3rd year or maybe in your Master of Science study program, and if somebody asks you what is the essence of linear algebra, why do you use linear algebra? If you don't say the essence is diagonalization, then you do not deserve to pass this class, because it is a single word, okay? It's the word of diagonalism, okay? It's diagonalization. So if you cannot remember this word, you really don't deserve to pass this class. But all this beautiful concept, a very useful concept of diagonalization, it is all built in our careful understanding or our careful teaching approach that we use on what the basis is, how we can transform from one basis to another, and how we can couple and decouple variables. Now, you are studying in electronics engineering, and you are going to learn very soon that the electric field and magnetic field, they are coupled together. So let me write these keywords. So we have some variables that are coupled, okay? What does this mean? This means that if the electric field changes, magnetic field is born. If the magnetic field is born, you get electric field back again. So this is called coupling. Untitled Matrices. Then this coupling, so which you traditionally you are going to see in electromagnetic field theory or in electromagnetic waves, which are probably wonderful courses that you are going to learn a lot. You'll see the coupling there, but you're also going to learn in linear algebra that it is very essential to do decoupling, because sometimes if you have decoupling, because sometimes if you have several variables that are intermixed together or coupled together, it is much easier to decouple them, which is an approach doing this, by doing the diagonalization. Okay? So we are trying to build up all this, you can ask to yourself, why are we doing all this work? Why do we need the basis? Why need the coordinates? I can say to you, you are doing it for this. Okay? How we do it, we are going to learn, and it is our job to do the best to explain this to you. Any other questions? Is it clear? So this word, diagonalization, don't forget. I had a friend who applied for a job somewhere, and they asked him, what is the essence of Fourier transform? He forgot. He did not get the job. Okay? So there are some keywords which you should never forget. And if it is anything regarding linear algebra, it is this word which is here on the board. Now, let's see another linear transformation. Let's assume we want an LP which rotates a vector by an angle theta. In the previous session today, we saw that, or we talked, and we look at the examples, that if we apply a matrix to a specific vector, it rotates it, and it changes the magnitude. Now, the rotation, how can we describe? So, this is the linear transformation. The next question is this: what is A? Okay? Why do we need A? Which is also this A here. We need A because we are very good at implementing or multiplying matrices with certain data sets and seeing the difference. That's why we care about it. But now, we want to rotate by angle theta where? Let's assume we want to rotate it by angle theta in R squared, which means that in two-dimensional plane, which can be described by a Cartesian coordinate system, x and y. And how can we find this? This A would be equal to the linear transformation on E1 and linear transformation on E2. Okay? This is what we need to do. What is E1? E1 is this vector here, and E2 is this. So we have this vector and this vector. Now, what happens if we rotate the vector 1, 0? So if we rotate the vector 1, 0 by angle theta, we get this. So if we have this vector, then what is the projection of this vector along the x-axis? So the projection of this vector along the x-axis is going to be, so this linear transformation on 1, 0, this is going to be equal to cosine theta. And the projection of the same vector on the y-axis is going to be equal to sine theta. Similarly, if we apply this linear transformation on 0, 1, we get what? We have this vector which is going to rotate on this side, and the projection along so this is again angle theta, and the projection along the x-axis is now a negative value, which is minus cosine theta, and this is going to be sine theta. No, we'll say this is minus sine theta. Okay, so apparently, finally, the matrix A, which is equivalent to rotating a vector by an angle theta, it can be written as cosine theta, sine theta, minus sine theta, and cosine theta. Now, I can ask you the following. What is the determinant of this matrix here? Сага детерминанта матриця two?
No.
That's true. So determinant here is equal to cosine squared plus sine squared. Which is equal to 1. And we know what this matrix was, right? In the previous session, we called this unimodular matrices, and they are very useful because we saw an example of how unimodular matrices, how they can rotate the vectors in a specific domain. Okay, this was the linear transformation, and then, regarding yes.
Why are the coordinates of the second linear transformation minus sine theta and cosine theta? Like cosine is in the negative part.
This is a good question, so let's look together. So, you're asking about this one, right?
Yes.
Okay, so the original vector, it is 0, 1. So the x-axis is, the x value is 0, the y value is 1. This is what it is. And we just rotated from the vertical direction by an angle theta. So what is the x value? Is it positive or negative?
The x value is negative.
It's negative. How much negative? Чего? Q bringing 2. Algebra practically bringing 2. Since this angle is theta, this side, so imagine this is a circle with radius 1, okay? If this is a circle with radius 1, this one, it is sine theta, and the projection down here, it is cosine theta. Now, if we rotate here by an angle theta, we are moving minus sine theta to the negative value. Is it clear?
Okay, yes, thank you. I got it now.
And also, we have the cosine value. I wish I could draw this a little larger, but I believe this is clear, right? Yeah, maybe I should do a better job, which includes drawing this, and this goes here, and if this is length 1, this is 1, this is cosine theta, this point here, it is sine theta, and this vector 1, when it is rotated down here, this is minus sine theta as a magnitude, and this is equal to cosine theta. Okay, so this is what we're trying to say. So this side here is equal to this side here. Okay. This magnitude, we get it here. But the y-axis, it will be cosine. Is it clear now?
Yes.
Okay, so here we have a unimodular matrix which has this property of rotation.
Professor, may I ask you something?
Sure.
Is the determinant always 1 in this case?
Say it again.
the determinant is always 1 in this case?
Apparently, yes. We are saying this is true for any angle theta, and if you check it, it's cosine squared plus sine squared. So rotation matrices, their determinant it is 1. Okay? Yeah, so this is regarding the rotation matrix. And then, let me see. This is my 2, my 3. So these are the linear transformations, and now I want to talk about the coordinate change. I want to erase this one because I want to use the center of the board. Okay, so we said that we wanted to change the coordinates from one domain to another. Let's assume for a moment that we have here the standard basis, and this standard basis, it is, what is the basis for the standard one? It looks like this, right? So any vector that is here in this domain, we may be interested into trying to determine how this one looks in another basis. Let's assume we have another basis which is here, and it is described by vectors which is 1 to -1 to -1, 4, 3 to 1. Imagine that we have a vector in this new basis, which is different from the standard one, and let this vector be, for example, 4, 1, -5. And we can have another basis here. So actually, for the three-dimensional space, we can draw an infinite number of bases. Let this be 1 -1, 0, 2, 0, 1, 3, -2, 5. So this is another basis. Let's consider this one basis B1. Okay. Let this be basis B2. Now, the biggest question that we might come up with very soon is the following. First of all, this is a vector. So let's assume we have a vector V, which is equal to 4, 1, -5, according to basis B1. Okay, so this is a given, and we may ask, what is this vector V in this basis B2? So how can we find this? Okay, first of all, it is always good for us. In the examples we solved before in the previous session today, we noticed how a specific vector or the same point in space stays the same. So it's the same as, imagine for a moment. This point in space stays the same, but the projection here and here is going to be different. So this would be another basis, which can look like this. And the projection on the red lines is going to be something like this. Okay? So these two vectors would give this point, and similarly, these two vectors in this Cartesian coordinate system would give the same point. So imagine you are fixed in space in one point, and then you have the basis sets which are rotating, or which are everywhere. And now, the point is that how can we represent a single point according to this basis, or what is the projection in B1, what is the projection in a standard basis, and what is the projection in basis B2. Now, first of all, we can also ask, we know what, we are very good at perceiving the standard basis. So why don't we have a look of what this vector looks like in the standard one? So, any volunteer wants to help me here? Or I'll pick someone. Albino or Besmir? We haven't heard Besmir much. Besmir, can you help me here for, I'm going to ask you a couple of questions. Besmir or Albino? Let me pick Albino then.
Yes, Professor.
Thanks, Albino. So let's have a look here. So, can we first identify together how does this vector, how is this one projected in the standard basis? We could say that vector v, it is equal to 4 times the first column, 1, 2, minus 1, okay? This is what it is, right? Plus 1, multiplied by 2 minus 1, 4, plus the projection onto the last column, which is minus 5 times 3, 2, 1. What do we get here? 4, 12, minus 3, well, this is 4 plus 2, 6, minus 15, minus 9. You will get minus 9, minus 3, minus 5. So we get here minus 9, minus 3, minus 5.
And now we write that SB, or what should I say, is equal to 9 times, minus 9 times 100, plus minus 3 times 010.
So this is true. So this is the projection minus 3 times 010 minus 5 001. So this is the same vector v, right? Then, but you know, let's have a look at this one. You know, this looks like, we know it from matrices, that the linear combination, what is this? This is a linear combination of some columns, right? We used to say that the range of a matrix A, it is equal to the linear combination of all the columns. So now, most probably, it looks to me that this expression, this part, we can write this one again as 1, 2 minus 1, 2 minus 1, 4, and 3, 2, 1, multiplied with 4, 1, minus 5. Would you agree with this? So this is true.
Yes.
Oh, thanks for confirming. So
Professor.
Yes.
Sorry to interrupt. Can you explain, like, what's the meaning of the calculations we did here? Like v, is that v times b1 in the first one, or is it the? I don't really understand.
No, this is the vector v. Okay, and the vector v, according to basis b1, is equal to 4, 1 minus 5. Okay, that's what we're saying, which means that the projection on this first column is 4. The projection on the second column is 1, and the projection on the third column is minus 5. That's what we mean. Similarly, in this basis, this vector is 9. The projection on this is minus 9. The projection of this vector v onto the 0, 1, 0 is minus 3, and the projection minus 5 is this. Okay.
How did you get those numbers again, Professor? Like minus 9, minus 3, and minus 5. How do you get those?
Because I was trying to. So if this is, first of all, how do you get this? Normally, if you have a vector which is 3, 4 in Cartesian coordinate system, what is this? This is equal to 3 times 1, 0, right? Plus 4 times 0, 1. This is it. This is how we describe. And let's not forget how we define the coordinates. The coordinates are these, if these are the coordinates, then this point in space, where do we find it? We find it by multiplying the first projection, the first coordinate 4 times this vector, plus 1 times the second vector, minus 5 times this vector. Let's not forget that we used to write any vector v as alpha 1 v1, right? Plus alpha 2 v2, plus alpha 3 v3, where v1, v2, and v3, they were a basis, right? Sorry, this is v1, v2, v3. So if this is a basis, then any vector can be written like this. Is it fine, no?
I think yeah.
Okay, so and then we solved an example in the previous session where we projected a single point in space onto two different bases. We're going to see a few more examples, but if this is true, this looks like the linear combination of these columns. It can also be described like this. So this expression, it is equivalent to this. Okay? Would you agree with this?
I think yeah, but Professor, so we can conclude that like the projection of V onto B1 equals the projection of V onto the standard base and onto B2, right?
Yes.
Okay.
Exactly. Because it is the same, what does not change is one point in space, okay? Then the bases might be looking different, okay? They might be looking exotic or different or weird. But that point is the same point in space, okay? So in principle, it looks like if we are on basis B1, we can find the projection on the standard basis by multiplying this matrix by the projection here, okay? So apparently, this is what we get here. We see that any vector x would be equal to P1 times the coordinates of x onto the basis B1. We got it. So, which means that from here, we can move to the right using P1, okay? Now, there is no difference between P1 and P2, so similarly, we can also move this way with P2, okay? And then, let's assume for a moment, so it looks like these two vectors, they are connected like this. So this vector, it looks like this in the standard basis. Now, let's give another vector, which is 5, 7, minus 3. 5, 7, minus 3. This is a vector in the standard basis. The question is the following. How does this point in space look like here? How would you answer this one, Lou?
That's a nice question. So I have to think about that.
Okay, give it a try.
I think we do the same process we did with V. Like we take 573 and do a linear combination of that with the standard base.
So allow me, yes, let's do it like this. X, normally, if we write nothing here, this is standard basis. But let's formalize this one. Let's say that X, according to the standard basis, it is equal to P1 times X according to basis B1, okay? Now, so we are given this, and we find this. Imagine for a moment, now we are given the X in standard basis. Or why don't we do it like this? Allow me just for a second, if we do this. What would you get if we multiply both sides with P1 inverse? What can you say to this one?
Well, in the right hand side, we get an identity matrix.
Yes.
And the left hand side, we leave it as it is.
So apparently, P1 inverse times the projection of any vector in the standard basis will be equal to the vector projection in a different basis. Okay? So this is what we observe, which means that we can move from this side to this side by multiplying by P1 inverse. Okay? So in this case, if we are given the matrix P1, we can try to identify the P1 inverse, and if we follow, we can write the P1 inverse directly, and this is equal to P1 inverse is 1 over 4, 9 minus 4, 7. 9, sorry, minus 9, minus 4, 7. 10, 4, minus 6. 7, 4, minus 5. So this is the P inverse, which means that, wait a second, I made a mistake here. This is a huge mistake because P1 goes this way, but P1 inverse will go this way, okay? So if we are given this 5, 7, minus 3, this means that this new vector, we have 1 over 4, or allow me to do it on top of this. So this P1 inverse, let's multiply this with 5, 7, minus 3. And what we get is the following. It's 1 minus 1, 2. So we can check, we have minus 9 times 4 is times 5, minus 45 plus 70 is 35 minus, so this is minus 45 plus 70 minus 21. This means that this is 60, what is this? So this is really, we get 1, then the next value, it is 4, is 5, 7, minus 3, minus 5, it's minus 1. Okay, so this is what we get. We get 1, minus 1, 2. So we obtain this by moving this way, okay? So, and similarly, if we can move this way, well, let's do it in this way. In fact, let's say that this is 1, 2, minus 3. Imagine that we have a vector 1, 2, minus 3 in the basis P2. How would this vector look like in basis B1? How can we do this? We have 1, 2, minus 3. In order to find how this vector would look on the other domains, what we can do is that initially we can multiply this with P2, because we will get this vector from here, we will project it on the standard basis. So P2, and by the way, we have to check whether the determinant here is different or not, because we just randomly came up with these numbers. So let's have a look inside the determinant here. Apparently it's 9, okay? The term there is 9, which means that it is different from 0, so it can be used as a basis, okay? It's always, we should always check for these, and let's do here 1, minus 1, 0, 2, 0, 1, 3, minus 2, 5, and yeah. So what do we get here? This is equal to It's 1, 2, 3, 1, 2, minus 3. So this is 1 plus 4, it is 5, minus 9, it's minus 4, minus 1, plus 6, this is 5, and 2 minus 15, it's minus 13. So apparently this is minus 4, 5, minus 13. This is in the standard basis. And now, in order to see how this one looks into the basis B2, we multiply. So let's see again, this is P2, this is X according to basis B2, and here we get X according to standard basis. Okay? Then we want to go to the other basis, which means that here we have to get okay, so let's see what we get here. We have minus 9, minus 4, 36, minus 50, so we get minus 14. Then here we have 1, minus 91, so this is 140, what is this? 141, minus 36, this is 105 divided by 4. Is this correct? Yes. Minus 105 divided by 4. If I check this again, this is 36 plus 50 minus 50. No, wait a second, plus, wait a second, no, this is a mistake. This is 36 plus 50 minus 91. Okay, we can correct this. 91 minus 86. So this is 91 minus 86. We get 5 over 4. Minus 5 over 4. You can check, maybe there could be some small mistake, but I believe this is better. And now we divide by 4 here. So in principle, we are going to have minus 1. No. Minus 1, 4, plus 5, minus 13, 9, minus 13, minus 4 divided by 4, minus 1. Here we have minus 1, and then we have 7, minus 28, minus 30, plus 65. So here we get 65, this is 7, 7 over 4. Okay, so the numbers, I hope we did everything correct. There could be some plus minus 1, so this is, let's not forget, this was the standard basis. This is the P1 inverse, and this is the vector in the basis P1. Okay. So this is a vector, this is a vector, this is a vector, and this is another vector. So finally, it looks like here we have minus 5 over 4. Minus 5 over 4, minus 1, and 7 over 4. Okay, so it looks like we can link this vector, we can find it. So now we can write, you can actually, maybe it's better if you do it like this. This vector is equal to this projection in the standard basis, and it's equal to this vector in the basis B1. And finally, what we observe here is that x, according to the basis B1, it is equal to P1 inverse times x in the standard basis, which is equal to P2 times x according to the basis B2. Okay, so now I want to ask you, do you have any question?
Professor, what is in between P1 inverse and P2?
Sorry, say it again?
What's in between P1 inverse and P2? Is it like multiplication or?
They are just multiplication of two 3x3 matrices. That's it. Okay. So similarly, let's have a look again. Wait a second. So similarly, if we have any vector, let's assume that we have a vector which is given to us in basis B1. Okay. How can we find how the vector looks in basis B2? If the vector is in basis B1, that means that we are on this domain. Okay, let's have a look. So this is B1, right? And this vector is here. How can we bring it to the standard basis? We have P1, right? So if we are given a vector in this domain, in basis B1, we can move to the standard basis, multiplying by P1. So here we multiply with matrix P1, and matrix P1 is this one here. Then we are on this domain. Once we are in this domain, how can we jump to domain P2? We have to come backwards with P2 inverse. Okay? So we come this way with P2, we go backwards with P2 inverse. So if we multiply here with P2 inverse, we can get how the vector x looks like in the domain P2. Is it clear? What we can do is also the following. Imagine for a moment, we may come up with another basis. So, but let's look at this one. The standard basis, we are keeping it in the middle. B1 here, B2 here. We can come up with another basis, B3. Sorry, so this was B2, basis B2. We can come up with another basis, B3. And this B3, we can go up using a matrix P3. This is how always happens. Always, το elementet e bazës përdorë si matricë për të kapërcyer direkt të baza standarde. Okay? So you see here, we go with P1, here we go with P2, here we go with P3, but from the standard basis to B3, we come down with P3 inverse. So this would be the P3 inverse, and this is the P3. Okay. So again, if you want to jump from here to here, the path that one has to follow is that from here you apply P2, and then you look at the possible path, you go with P3 inverse, you get it. Okay?
So each base, let's say, jumps to the standard base.
Yes, you use the standard base as a bridge, you can say so, yes. And then you have to look at the possible paths the same way that you can look at the flow chart. Is it clear?
I have a question about the P1 inverse. Like, where did we get the values?
The P1 inverse, that's a good question. I had calculated this at home, okay? I had just calculated it. If you want, we can calculate now the P1 inverse. If you like, we can do it right away. Would you like us to do it now?
O profesor, s'besoj që ka nevojë se procedurën e dim, vetëm që ka kalkulime shumë.
So yeah, it's just it's just some there's a specific procedure which takes a little bit of time, but it is doable. Yes, we can skip that. Okay. Any other question? Anything which is not clear? Okay, so if you have no more questions, we can give another break.